All right, let's first look at how to approach this problem in a way that makes a lot of sense and leads us to the incorrect answer. And I'm not even going to find the answer because it doesn't really matter what the numbers are, as I have mentioned to you all before. So a lot of times people will look at this and they'll be like, okay, we know that this 2 kilogram object is kind of the driving force, right? More precisely, it's gravity acting on that 2 kilogram object that's sort of driving all the motion that would be involved in a problem like this. And let's forget about the fact that there are some things we don't know that I didn't tell you. One of those things is there any motion to begin with? It doesn't really matter. If we're trying to find the acceleration, we can deduce a couple of things from this right away. Number one, in the absence of either gravity or this 2 kilogram object here, there isn't going to be any acceleration at all. So if there's no object, there's not going to be any acceleration. And if there's no gravity, then there's going to be no acceleration as well. Right? So we know gravity and this object have something to do with what's going on. And based on that and the direction that the rope or the string is going, we can guess that our 4 kilogram object is going to accelerate in this direction. So that means if it's at rest, it'll start moving to the right. If it's already moving to the right, it would speed up to the right. If it's moving to the left, then it would slow down and eventually reverse direction if nothing changes about this scenario. Okay, so then what a lot of people want to do is they want to say, all right, well, what we need to find forces. That's what we're really looking at here. And so, what's the force? Well, the force here is all coming from this 2 kilogram object. So, if the force is coming from gravity acting on this 2 kilogram object, then isn't it like this whole thing? Right? I mean, that's how you figure out what the force of a mass is, right? And so if F equals mg, then that's 2 times 2.0 times, let's just say 10. So that's going to be 20. And if you like remember the units here are kilograms in meters per second squared, and the units for force are newtons. So we have a 20 Newton force. That 20 Newton force is going to be acting right here too, right? Because there's that connection. There's the rope, which is like basically transferring the gravity that's acting on the 2 kilogram object. That's just sort of transferring it to the 4 kilogram object. And we know Newton's second law says force equals ma, and we know that the mass is 4 kilograms, so our acceleration should be about 5 meters per second squared. And if you used 9.8 here, then you're going to get an answer that's close to 5, but not exactly 5. And this all makes a lot of sense, and it's very intuitive, and it's not right. It's not accurate. And the reason that it's not accurate is because there are a few assumptions that are being made here that are not correct. The big assumption is that the force acting downward on this 2.0 kilogram object is going to be the same as the pulling force that's acting on this 4 kilogram object. That is not necessarily the same. And I'm going to explain that in a separate video, because I think probably some of you have gotten to this point. You got this answer of 5 or close to 5, and I want you to have a chance to kind of think on your own about where you might have gone astray, given that one hint that the downward force from gravity acting on the 2 kilogram object is not the same as the force that's going to be in that rope or string, right? So you can work on that for a little bit, and then look at the next video for a full solution.